The scope of this lecture 24 is inheritance, polymorphism, derived classes. So there's a lot of concept, lots of terminologies. We're going to take the time to explain them. So let's talk about inheritance and polymorphism, derived classes. So this is by and large the principle you see in OOP. So what does OOP stand for? Object-oriented programming. Okay, object principles, or sometimes they call it programming or program, object-oriented programming, OOP. So there are three principles. One of them is data encapsulation, which is something that went through last week or 2 weeks ago. This is the second principle, which is inheritance. Polymorphism is number 3. Okay, and this derived class is the outcome of these two. So we're going to talk about all three of these. So you can think of inheritance as new classes created from existing classes. So kind of like having a set of genes. Okay, if we're to make analogies in your grandparents give rise to your parents, and your parents give rise to you, your siblings. That's the inheritance right there, right? So when you create a new class, when you have a child class, a lot of features in that child class inherit, okay, from your parents. So inheritance means passing down. Okay, so these are very important and very, very powerful concept because you're passing down not just a set of properties, you're passing down also the behaviors as well. So you can probably see this in your uh, interface polymorphism, right? So whenever you define an ADT, you create your interface in Java, and then your solid or concrete class will then implement, right, your inheritance. Your implement your interface. Uh, as in inheritance, we don't use implement. Okay, so implement is a keywords in Java that deals with interface. In inheritance, we use a keyword called extent. Okay, so this is class. This is inheritance. Okay, so this concept of extent, again, this is the implementation detail. I just want to stay higher level than that, 30,000 foot view. So that's new classes created from existing class, or existing class passing down the traits to their own, right, child classes. Okay, and this is a concept that basically involves absorbing attributes and behavior. So attributes means properties, and behaviors means functions or methods. Okay, functions or methods. Okay, so this is attributes means properties. All right, so that's inheritance. Any questions about inheritance? All right, let me erase this. Let's go over polymorphism. So polymorphism is another very powerful concept. So let's break this down in Latin. Poly means many, right? Morphism means phase. Okay, so morph meaning assume certain shapes or forms. So if you put two together, this is the ability or a pattern or paradigm that allows you or program to assume many different shapes and forms at runtime. Okay, so this is a very powerful runtime behavior. A lot of times they call it late binding. Okay, and inheritance is more about early binding. Early binding is another term. I think computer scientists they coined very many terminologies to compile time. And late binding means run time. Okay, so this means that a certain object that looks like an object at compile time could become a cat, could become a dog, or anything. Okay, so this ability to kind of morph, right, into certain shapes and forms is what we call polymorphism. So this is a huge, huge advent or powerful forward-thinking ideas that exist in C++ that does not exist. They do not exist in C, right? That's why C was limited, and Brian, the inventor of C++, right? The Shoestrap, he's the inventor, coined this thing called term called OOP, object oriented, treating every object, as a separate entity with its own, you know, kind of like a struct, right? But these objects can inherit from each other. These objects can also assume certain behaviors and shapes at runtime to morph into something. And all of this, right, got into um, pretty much the modern day OOP languages, starting with Visual C++ by Microsoft, Java, right, back in the early 90s. And then there's a whole lot of, like, even JavaScript these days. These are OOP. Python is OOP as well. So I'm going to pause right here. Any questions about polymorphism? Again, this is still on a very high level. Let's talk about derived class, right? So derived class means a child class. Okay, child class. This is a class or an object that inherits from the parent class or superclass. So whenever you have a derived class, it's implicit that there is a parent class somewhere. So if I were to draw something like this, where this is a derived class, there is a parent class somewhere. Sometimes we call these superclass. Sometimes we call it base class, base or superclass. And some of your base class, superclass, maybe this portion of it will be inherited by your DC, okay, derived class. So this is through inheritance, okay? And depends on how you set it up. The factor, this polymorphism also, plays an important effect. And polymorphisms use whenever there's a virtual table that is involved in governing what this method and behavior should be in a derived class. And this is through use of virtual and pure virtual facility in C++. So these are keywords. Okay, so the power derived class could assume either inherited set of properties and behaviors, or it could assume a polymorphed, right, properties and behaviors, depending on how you set it up. All right, so I'm going to pause it again right here. Any questions about derived class? Yep, so is it good? Okay, so we spent a lot of time on this page. Let's move on to the next page. So it turns out, let's go back to inheritance. It turns out in C++, there's multiple inheritance. There's single inheritance, multiple inheritance. So if I were to draw your attention to this box, this is our, let's just say base class, okay? Base class. So this is almost like the mothership, right, of everything. Off of the mothership, there's individual ships and vessels that comes out of it. You could have a single inheritance. By the way, this arrow, which is a open arrow, not a closed arrow, it looks like this. This is a universal model language style of drawing inheritance. This arrow going up with a open arrow, not the filled arrows, represent a single inheritance right here, because there is only one child class or derived class here. This is what we call single inheritance, right? There's no questions about it, right? Single, right? There's one single chain going up straight up into the base class. Now, multiple inheritance means that there is, if I draw your attention here to this box, that you could actually have your derived class or child class. I'm going to call it derived class, okay? DC. There's base class number 1. There's base class number 2, where you can have multiple inheritances. Well, inheritance is singular, so it's multiple inheritance, meaning class inherits from multiple base classes. This is very possible. You can also have 3, right? And then what's crazy about this is you can also be, your DC could also be the base class of another inheritance pattern and this is DC2. This is DC1. Does it make sense? DC1 could be base class number 3 for DC2. So it's very crazy. You could get into a diamond multiple inheritance patterns where you have something like this. Let me pause right here and ask you, if you see a diamond right here, and let's say your angle is to create this derived class right here, all the way on the bottom. Do you see any pattern right here? This is a diamond. They call it diamond inheritance. What comes to mind, immediately comes to mind to you when you see this diamond inheritance? Is there a problem? What is the problem? Take a guess. All right, some of you probably already know. You're just too shy to talk about it. But take a guess. What do you think? Diamond inheritance. By the way, I should have made this into a participation activity. Well, there's one big problem right here. If you're a DC right here, okay, do you know, let's say DC has a whole bunch of properties and behaviors. Do you know if this blue, that I mean, this orange property, is it coming from here, or is it coming from here, or is it coming from here, right? So this question, right, of provenance, you guys know what that is, right? Attribution. Like, where is the property coming from? Is it coming from this base class, or this super class right here, base class 1, base class 2? It creates a provenance issue, attribution issues. And this is a source of bugs, a lot of bugs. I mean, if you had an issue with this class somewhere deep down at runtime in your system, you're trying to locate your bug and you don't know where this is coming from. And it becomes super complicated, through polymorphism and inheritances, because everything kind of gets mushed together. I mean, you can have the best logging system, logging the heck out of your class and say, hey, every time this feature gets inherited, I'm going to print, system out print line, right? That's all we do, right? But there's a lot of problem with that. One is you don't put logging in the production system to slow your system down. And even if you turn on debugger, there are certain sets of features and behaviors that are coming from somewhere, but you don't know, through this diamond pattern. This is the reason why Java completely gets rid of the multiple inheritance. Java doesn't have multiple inheritance. There's only single inheritances here. Okay. All right. So yeah, so I kept going back to Java, and I guess when I say implement and what do you call it? Extent. Yeah, these are for data structure classes, and I think since we're talking about C++ here, and these things don't really apply. But we'll talk about how we inherit, how the proper syntax plays out in C++. All right, any questions about multiple inheritance, single inheritance?
Yeah, I have one. Should we just strive to use single inheritance then and try to avoid multiple inheritance whenever possible in C++?
Yes, I would say the standard practice and the best practices moving forward is, do not use multiple inheritance if you don't have to. Yeah. And even if you use multiple inheritance, don't get into this diamond structure here. Okay, so once in a while, I think it's okay to have maybe 2. That's totally fine, right? You can say that this is maybe parts, and this is the body, and this entire thing is the car. I think this is fine, but yeah, don't get into like second tier multiple inheritance. This becomes an issue moving forward, and this is the type of design pattern that is frowned upon in the industry. All right, any other questions? Good, cool. So there are 3 types of inheritance. I'm just going to lightly touch on these. Because this is, first of all, everything is public in Java, but in C++ you see this delineation. The reason why you have this granularity is C++ came first. right? Introduce a lot of great ideas, but over time, ideas like multiple inheritance is becoming so unpopular, and forthcoming languages they just got rid of it. And in you know Java, uh, yeah, you don't really see a lot of these either. Although they still work, right? So if you have public inheritance, meaning every single trait that your derived class gets from the parents, they are publicly accessible. And then private means it could only be accessible by the base class. So there is certain sets of restrictions that you can do. You can think of, information only get passed down, and certain information due to private, public, or protected inheritance are only accessible by a certain member of your entire ecosystem. Okay. Yeah, I would not give you quiz on. I will not quiz you on this one, so don't worry too much about it, because I also don't find it really useful for at least for beginners to have to go through these. All right, let's move on. Any questions about this? All right, let's move on to it. So here's the inheritance concept involving three objects. So you have polygon, rectangles, and triangles. So the first thing we want to do, hold on, let me go back. First thing we want to do is to define them, right? So in order to define these classes, and this is what we did, and you guys are all familiar with the syntax: class, polygon. Oops, hold on a second. Let's go back. Class polygon, it has some private info. This member private infos are number of vertices versus number, basically number of edges, right? How many edges you have. Sorry, not edges. Edges is represent these lines in data structures. I'm talking about these nodes, right? These nodes on the. So rectangle has 4. Polygon may have 4 or 5, right, depending on how many sides. So this is how you define polygons, by the number of vertices and the coordinates, x and y coordinate that defines it. There's also a set method that defines the x and y coordinates plus the number of vertices. Okay, so that's that. So you can have polygon versus the coordinate usually sets it right in the middle. All right, so this is symmetrical. All right, so that's versus, and versus, sorry, not versus, but coordinates has x and y directions, right? This is a 2D. Okay, x and y. So that's polygon. You can have rectangle similar to polygons with number verses, coordinates, and set methods. However, your rectangle also has this area method that is particular to rectangle. And also triangle, having the same flow area, but the number verses, coordinates, and the set method as well. All right, as you can see, there is a lot of shear, right? At least the shear properties and behavior, right, that exists amongst the 3 objects that you see on the screen, right? The portion that are duplicated are namely your private member variables, numbers, x coord, y coord, plus your method called a public method called set, right? This is set method. And what is different amongst them is the addition of this area function or method in both rectangle and triangle. All right, and since this is a class definition or declaration, you see this colon sign, right? This is very important, okay? So I think I mentioned it before. When you have a class, you gotta have a semicolon here. If you don't have semicolon, your entire class declaration is not gonna be, it's not gonna work. All right, just treat this entire declaration as a statement that needs to have a semicolon at the end. That's why you see these. Okay, that's everything I wanted to talk about in this particular slides. Any questions? All right, so let's take a look. Can we simplify this? Right. The question is, can we simplify this? Yes, we can. Simplification means code reduction, right? Where can we eliminate code? Well, basically where you see the duplicate ones. Let's think about how we can simplify this, right? By consolidating this dupe, and this dupe, by dedupe it, right? Deduping means reducing code. It turns out what we can do is we can set up, let's just do this, inheritance structure, right? So in the previous slide, everything is separate. right? You create the three, pretty boring. It's the three instances, their blueprint, if you will, that has no linkage between the two other than a whole bunch of duplicated code. So you can write this all day, right? Producing a lot of these duplicate code. But if we do it smartly, right, using inheritance, then what we want to do is set your polygon, right? Polygon has n number of sides. Rectangle has four sides, n equals 4. Rectangle, n equals 3, right? 3 sides. So this polygon literally has a couple of properties and behaviors, namely your protected data member, your num versus x core, y core. They could be protected as in, I just want the polygon's derived class or the derived class of polygon to have, but I don't want anyone else to have access to it, right? This is important because in Polygon, remember, all of your member variables are set to be private, right? So you want to keep that information only to yourself. But however, since you're making this, right, using this inheritance pattern, ideally you want to use Polygon as your, what do you call it, super class, right, or parent class. You would want these member variables to be protected in scope. And then same thing with your public. Public, there's no change here, this method. Make sense? So that's your polygon, right? Now, let's move on to what we do with our rectangle. And yeah, so this is the before and after, right? Remember what we had before, right? You would write rectangle protected. Okay, so this is kind of boring, this entire pink area. Now let's look at this yellow area where rectangle is literally a derived class of polygon. So what you do in Java, you would have written extend, right? But in C++, instead, you would have this colon right here. And then you have to specify, right? Is this a public inheritance, protected inheritance, or private inheritance? We don't ever use private inheritance. To me, that's singleton. That's some design patterns. And that's a little more advanced to talk about in this class. We use public. So you have class rectangle inheriting off of your polygon through public inheritance. And what gets inherited? Net new inheritance object. By the way, every function is an object. That's what I'm used to call it. Your float area method is the net new addition. Make sense? Because everything else is already there, right? Like your protected member variables, everything's there, including its public void set. So all you need to do in this grossly simplified version, right, of your inherited derived class called rectangle, this is all you need to write, right? Nothing else. And you can assume, and this is the case, that everything Polygon has in terms of its protected member variables, in terms of its public member variables and behaviors or methods, would have been inherited by your rectangle derived class. Okay, so any questions about this? Right, this is the key right here, right? So what is the immediate benefits you see in having this?
Less code to write.
Yeah. What is the immediate outcome of having less code in the system?
Less places to fail.
Not really. I mean, you're still getting a lot of code in when it's compiled. The logic is still there, but what you end up with would be less footprint, meaning your exe, right, or DMG when compiled, because eventually this is going to compile into a library. It could be a lib, right? Their footprint or the size will be a lot smaller. Okay, and so that's a good thing, right? Because you have a smaller footprint in executables means that they run faster. That's it. Your operating system, by and large, runs faster with smaller footprint executables versus a large footprint because executable, because these larger footprint executables, they have to be loaded right in memory. So memory consumption goes up on larger footprint executables, and they just run slower. And so that's number one. Number two is less code to write means easier to maintain. For developer productivity, there is a benefit there, right? As you can imagine, less prone to making mistakes. So developers a lot of times they copy code from left and right. Not all the developers, right? I don't like developer copy code. That's code monkey in a sense. But when you have to, when you don't have to copy as much code or write as much code, your code becomes a lot simpler and easier to maintain. Period. Right. So there's a lot of benefits in going this route right here. Okay, versus going this route. All right. Questions? So good? Cool. Let's move on to the next one. We are halfway through. So you would do the same thing with triangle. Okay, so in the triangles, you have this version versus this version right here, right? The only thing you need to do net new is your public flow area because this part exists in triangle, but not in polygon. Any questions about this? So this is inheritance, public inheritance in the upshot, right? Nothing else. You don't have to write anything complicated, but notice your inheritance scope is a colon, okay? It's a single colon, not double colon. Double colon means scope. Single colon means inheritance. Okay. All right. And then obviously the semicolon at the end, right, of your class decorations. Let's move on to the next one. So this is another one where you have point, circle, and 3D point. Now they all have certain properties, right? A point is, you can think of it as a 1D, right? One dimension. Circle is a 2-dimension. And obviously the 3D point is 3-dimension. Okay. So you can think of it as a pyramid or something, whatever. So it's pretty obvious that for each, when you're dealing with this 1-dimensional object called point, this is a class with certain properties and behaviors in them. The member variables will be x and y, right? This is the coordinate of your point. So you have a point, and this point has a coordinate system, x and y, maybe 5, 10, right? Whatever this is on the map. So that's a point. In addition to x and y, you also have setter, which is setting the value of x and y, period. Nothing else. Notice I didn't define any user-defined constructors. If you don't, then default constructor would have been supplied to you at runtime. Actually, compile time, not runtime. Okay, through your compilations. Okay, any questions about your 1D point decorations here? So this is your parent class. Okay, sometimes we call it super class. Yeah, I think in Java, they like to call it superclass because there's this thing called super, which refers to, if you're at the base class and you refer to invoke super means your immediate parent class. Okay, so single inheritance, you're calling the above. Okay, so superclass. In parent class, we use it a lot in C++. Anyway, so let's move on to the next slide. All right, so now we're looking at both circle and 3D points. So all you need to do is to define the net new element for circle. So what's circle? Circle has x and y, right? This defines the location of your circle. It also has this thing called, this is R, called radius, right? So we want this radius, which could be a double, which means there's decimal, I don't know, maybe inches or centimeters, millimeters, what have you. And it's a private information that we want to set in the circle, which means no one else should have access to R, but circle itself, the object of a circle. So this is public point inheritance. This is a public inheritance inheriting off of your point superclass. And you would do the same thing, right, with your 3D point. And by the way, this 3D dash point is a poor way of naming your class. Typically, you don't do that. You would do 3D, maybe point, or something like that. You can use a camel casing. But this best class, best practices. So class 3D point inherits off of point by having this private Z. So you can assume and not assume by doing so, since 3D points and circles all inherit some stuff from point through public inheritance, that whatever is here, they'll have it here too. Okay, when you run it. In other words, if you were to do a circle C, period, you want to instantiate the C or creating the C on the stack. This C would have access to Y and X. Okay, C dot Y and C dot. You can see out this, and then you see the value. The reason is because this X and Y's are passed down from your point superclass as a protected member, which your circle instance and your 3D point instance would have access to, right? That's called protected member access. Protected only for its offspring. Okay, so if you were to create another class that has nothing to do with point, and for some reason you want to bring points into fold, like in your class circle, not circle, maybe X, Y, and Z, class X, Y, and Z, you would like to have a point instance, and then you try to do P dot X, this is not going to work. And you try to do P dot Y, this is not going to work. Why? Well, this X and Y, this XYZ class is not inherited off of point. So XYZ instance would not have access to these protected member variables inside point. Make sense? So this is true for all of the OOP languages. As far as C++ goes, this is data encapsulation. Okay, ability to hide certain sets of properties and behaviors based on, one, their inheritance pattern, two, their access specifiers, right? When you declare these member variables and methods. All right, I'm going to stop right here. Any questions about this? Yeah. Cool. Let's move on to the very next. Sorry, hold on a second. Yeah, let's move on to the next page. All right, so this is inheritance in the offshot. There are two types. One is the augmenting the original class. The other one is more about getting more specific about the original class by extending it. So the first inheritance patterns goes like this. There's concept of augmentation, meaning you're supplementing something, you're augmenting the existing class by giving it more. So this is almost like, having, a starting point, if you will, entry point, right? You want to, supplement something to it, right? Like adding rectangle and triangles, having, rectangles area and triangles area, right, as a net new. So you're adding, right? This is a net new plus, right? For circles and 3D point, circle is radius, right? And 3D point has, I don't know, cylinders or volumes, whereas point doesn't, right? So this net new addition is plus, is what we call augmenting the original class, right? So this is a one frequent concept that you see, or patterns you see in industries where you see inheritance exists for the purpose of augmenting the original class, period, right? So that's one use case out there, right? Can you think of another use case? Well, I kind of alluded to earlier, right? This is the first use case. The second use case is specificity, right, to make it more specialized. Let's see how this works in the next page. All right, I'm flying through these slides. Maybe we can get to the end pretty quickly, and then we'll take a break. Specializing the original class. Let's take a look at what is going on here. So in this inheritance patterns where we have complex number, you guys know what complex number is, right? So in mathematics, when you have 5 plus 4i, right? This I is the imaginary, is a complex number. So you have real number on this side and imaginary number with the imaginary, I don't know, I. So this imaginary number, it's imaginary. It exists to facilitate some mathematical computations in higher level math. And there's a lot of use cases in using complex numbers in computations. Okay, they do not exist in real life, but they simply exist on paper. Like I said, to facilitate computing, certain algorithms and behaviors in the field of mathematics. So if you look at how you can extend your complex numbers in C++ using inheritance, uh, one obvious thing you can do is define the structure of your complex number, which involves these two, right, components. But you don't want to do that because you don't know what this real number is and imaginary number is. So you want to create a class that encapsulate these and have these classes to be inherited off of your complex number. So this complex number could literally be just a shell, right, or skeleton code, skeleton code that consists of real and imaginary parts in it. So this real could be integer real, and this imaginary could be a string, right, that has a real number, and plus this concatenation plus an I, right? This I right here. So you can have these skeleton code and simply just inherit it by your real number. So this real number class, right, would not have this portion, right? It will simply have just the real portion. And this imaginary number would have this real portion be nullified or -1, whatever. You can set it that way, but it will just have real plus I portion of it. Yeah, it's kind of hard to illustrate. I have some examples. You can, in fact, Google search it and see how this specialization of the original class works in real time in C++. This is a very basic or classic, okay, example of how we can specialize our original class by making use of inheritance in C++ and also in Java as well. So not just C++. So this is a pretty prevalent approach in my opinion. Any questions about these two? Yeah, you can also think of this specialization applying to car, right? Where you can think of, let's say, I'm sorry, if you use augmenting the original class idea, where car is the superclass, and then you can have parts, being the subclasses. So these parts could be wheels, right, and the body of the car. It could also be the number like seats, right? So the sum of its part makes whole, and that would be the car objects on top. At the same time, you can kind of flip this around and try to specialize something. So it's almost like the bottom, the top to bottom approach, right, or top down approach. And this one is more like bottom up. You're starting with the bottom and you go up, right? Top down, bottom up. All right, I'm going to stop right here. Any questions about the inheritance concepts in general? Q. All right, let's see how many slides we have here. All right, so this is an example of multiple inheritance. You see base classes and derived classes, right? So base class is a parent class or a superclass, starting with a community member, and from community member down, you have more specialized, right, versions of community member. This alumnus is a single inheritance because it inherits from community member once, and there is no other base classes involved. So is your student. Student is also single inheritance. Okay, SI. Your employee is also SI. Okay. However, when you get to this administrator part on the bottom, this is multiple inheritance because this object inherits from both administrators and teacher. And yeah, this is not a good practice in general. We just talked about this, but you see them a lot of times. It's okay to do single inheritance. So if you see this chain right here, the provenance is very easy to determine, namely staff with respect to employee is a single inheritance. Okay, so when you have like multi-tier inheritance, what is associated with each object, you only look above once to, and that determines whether this is single or multiple. So this is a single inheritance because it's coming from employee. Employee is also a single inheritance off of your community member, so on and so forth. Any questions about this inheritance hierarchy? Right. One thing about this though, right? This is a fairly complex design in software. Design is important because by looking at each use case, you're able to formulate an overall abstraction of what the parent class or a base class should be, how many variables it should have, and the methods involving setters and getters for these variables. And that is important. This requires that you need to have a foresight into how many of these different base classes you have, right? How many, not base classes, but derived classes you have. And so thinking through all of the use cases, thinking through all of the requirements, business requirements, to come up with something that makes sense. So this is what we call software design. Okay. This is not implementation, but software design. This is an important skill set that as a software developer, you need to pick up on is to design this right. Because you don't want to write code only to refactor it later on. It's very costly. So this is another example where you see derived classes and their relationship to superclass. Okay. So you have student, the very first one. And in a more specialized version of a student, you can have graduate student and undergrad students. You can also have, other types of employees. They could not, they don't have to be a student. They could also be maybe a transfer student. I don't know. Transfer student could be a graduate student, could be undergrad. So even more specialized version of that. Shapes, you can have circle, triangle, rectangle. So this is again another specialization type of inheritance. You can have loan. By the way, these are all specialized version of it. Like account, a bank account. You can have checking. You can have savings. You can have CDs. Employees could be faculty members, staff members, temp. It could be custodians, whoever. Loans, you can have car loan, home loans, mortgage loans. Any questions about this? All right. Yeah, this is something that we already went through, right? To college members in a relationship in the inheritance hierarchy. This is an example of the shape that I was talking about. You could have, for example, shape be the parent class or the base, right? And all of a sudden, you can define their immediate next step, right? Immediate next a derived class being a 2D shape or 3D shape. A 3D shape could be sphere, cube, tetrahedron. 2D could be circles, square, triangles, right? So on and so forth. So this is how you would design, right, your software to begin with, assuming these various different objects. And then at design time, you can think of what variables, member variables, and methods that could be net new or plussed, right, into each of these base classes, not base classes, derived classes. And that's how you set up your entire program from the offshot, what it needs to look like, how many variables, how many different classes, how many different methods that you ought to have. And then you can decide based on their relationship, certain data needs to be obfuscated or maybe inherited or protected, such as bank account, right? And on the very top, right, you could have ATM machine. An ATM machine and bank account, they don't really ATM. They're not related, but then you can think of ATM having a set of different bank account with access to them. And what's inside the bank account? So this could be the has-a relationship, one to many. It becomes a lot more complicated when you start to get into a design. And inside bank account, your balances, right, and PII, these user info, password, right, these things are highly sensitive data that you want to reveal, that you do not want to reveal. They could be private. Okay, and these informations you may not want to be inherited, right? But only accessible through getter and setter and getters and setters through the derived class as the protected member. So yeah, there's a lot of these design choices that you can think of when dealing with a large ecosystem of objects and classes. All right, questions about this? All right, if not, then let's move on to the very next slide. So this is public inheritance in implementation details. Let's look at the specific because we went through this on a very broad stroke a couple of slides ago. So this is your student class, right? And it's doing a inheritance of, and it's a public inheritance of people. So literally, this is what you have. If you were to draw them in a box to represent these classes, this public inheritance, this is public, right? Assume this UML diagram. This is a class diagram, okay, in UML, Universal Modeling Language. This is student, okay? So student inherits from class. Do not worry about friend functions because this is an afterthought, in my opinion. Certain features in C++, even though they're still available for backward compatibilities, they are no longer in favor of being used in a modern code. You have private members of base class. They are not accessible from the derived classes though. So these are important things that you should know. So something about people, they could have their maybe age, maybe their date of birth. These are not inheritable if they were defined as private. So who can use them? People, right? Only the parent class. So you might be wondering, what is it used for hiding this information? All of them in there in the base class where your derived class would not have access to. Well, for security reasons. But you might be wondering, how would I be able to, how would a derived class be able to access them? The question is, you don't. They don't. Simply no. But you can define a publicly or protected accessible accessor method to get this out, right? Maybe through some computations. Maybe your accessor method is called get rewards, okay? Meaning based on your age and DOB, right? If you're over the age of 25, you get this specific gift card. I don't know. That sounds like a discrimination, but that's just one of the use cases. Okay, I'm thinking, but maybe certain advertiser wants to do something about that, and this get rewards is protected, right? So such that it could be accessible by students. Students would know, right, based on maybe enroll time. right? Whenever they enroll in the class. If you are, I don't know, you have been with PCC for 1 year, right? You get to register early, right? Than the newbies, right? You know what I mean? So get registration time, right? Could be a protected method inside this people class, but then registration time itself is private information, right? Anyway, so yeah, this is still on a high level because we haven't talked about how we get these private information into, right? These derived classes and also the parent class. So in terms of the 30,000 foot view of your class skeleton code, any questions about this high level? Right, remember this colon, what this colon means, right? There are two things. One is this colon, right? This is inheritance um, key syntax, okay? And also this semicolon. So please do not forget these two. Lots of times students make a mistake. They do double colons, and then they'll forget about this semicolon, right? And it's not compilable. Your code's not. This is a wrong syntax. Okay. Cool. So let's move on. I think we have only three left, 3 slides, 3 pages left. So this is derived class object. Students can be treated as an object of the base class, right? So this is literally what we say in computer science. We say student, right, is a people, is a relationship. I know this is not grammatically correct, but in UML and software design, we call student is a people. This literally translates into students is a type of people. And because student inherits from people. Does it make sense? People as the parent, students as the derived. Okay, so this is a relationship, okay, in software design. So S can be treated as an object of the people class if we do something like this, right? So we are dynamically instantiating an object called S, okay? And this S points to this new location. So whenever you do new, right, you're creating an object in space. This new bears a student as a data type and has a memory address 0FA5 in hexadecimal. And that new returns, this new operator returns the memory address to this S variable. And remember what a pointer variable means, right? A pointer variable is the data type of student type in this case, number one. Number two, a pointer variable of student type stores the memory address of a student object in memory at runtime. At runtime. And the value of this S is that memory address right there, right? 0FA5, right? I think that's what I had there. Does it make sense? This is dynamic memory allocation. Dynamic memory allocation here, okay? Which means later on you have to delete S, right? You have to do delete S IDM, maybe in the destructor of your code. But you have to do this, otherwise you're gonna get memory leaks. That's terrible. Leaks eventually gets into memory segmentations, which limits your computer's ability to run more code, period. Okay, so you don't wanna do that. Base class object cannot be treated as an object of the derived class. This means if we say student is a people, you do not say people is a, okay, this is dot 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 a, right? Student. You cannot do that. Okay. So while a derived class could be a base class, right? Student is literally people, not the other way around. You can't say people is student, because if you think in terms of specialization, derived class being the specialized version of the parent. Parent is not that specialized version, right? But the other way around, when you state the specialized version is inclusive, right, of your parent, then that makes sense. Okay. And this is a very important thing you have to understand, because if you don't, and you switch the order and try to, access, for example, your student S, right, from people, this path is no good. However, this path is good, right? Accessing people properly, assuming they are protected or public, from student is allowed, 100% allowed. Okay, allowed. Disallowed, right? Try to access the other way around, right? Does it make sense? So that's really what, sorry, there's a lot of writing on top. You can go back and play back this video to see what I wrote. But this is a very important sort of concept that you have to understand.
So that's an implicit type change then. Like if I tried to I could feed student into a function that wanted a people, that would be okay.
That's right. Yeah, because student is a people. So if you want to, so this goes back to, the shape and, one-dimensional shape, two-dimensional shape examples that I gave. Any derived classes would have access to any protected member or public member of your base class, not the other way around. So in other words, we care about the derived class because that's the one that you're using. Base class is just there, right, for the purpose of being inherited, period, and co-reductions. And there's lots of other benefits, but you don't really use the base class to access your derived class. You can't do that. Okay. All right. Any other questions? The C++, yes, C++ has a relationship. So has is basically your member variables. Has a, it's basically member vars. Okay, so you can say, this car class, right? This car class having, color, number of wheels, num wheels, right? So these member vars has a relationship. This means composition. This entire car class has a color, has a number of wheels, right? So yeah, that's another very important part of your design, right? Is a and has a. This has a versus is a. Where is a is inheritance, this has a is not inheritance but composition. Right, this is inheritance. This one is composition. Okay, you might be realizing, this far into the lecture, there's no coding. But you're absolutely right. I mean, this is conceptual understanding of OOP in this upshot. You have to understand the behavior. You have to understand the relationship among various different principles that I elicited so far to really understand OOP before you start to code. Once you get into coding, once you have a solid foundation, then it becomes a lot easier and also sensible in a way to help you design and code faster, period. Any other questions? All right. Let's move on to more slides. 17. Yeah, so we're talking about protected inheritance. This is the intermediate level protection. You can think of public inheritance having the maximum amount of exposure for from which your public or protected member variables, even methods, would have been accessible by your derived class. Protected inheritance has limitations on that. So intermediate level of protections, in a sense, then you have to basically refer to the public and protected members of the base. Sorry, I just keep pointing the wrong button. Note that protected data, just like friend data, breaks data encapsulation. So yeah, there's a lot of these things that behaviors that You just have to kind of remember and memorize. So I'm not really keen on using protected inheritance at all. Or even the most restrictive of all is called private inheritance, where you would say, this is your class X dot, right? You'll write private or protected here as the inheritance keywords, and whatever class that you want, maybe protected class Y. Yeah, I don't really use these two, but they're just there for your references if you want to get into more of this. There are more of this if you get into, let's say, financial software applications. These things have very sensitive data encapsulation needs and requirements, and the use of these protected inheritance and private becomes more paramount. So this is an example of some of the high-level, nuts and bolts regarding your regular, public, protected, and private inheritance patterns right here. So I decided to cut and paste this entire image there of the differences in its upshot. So it's a lot easier to just look at it versus reading that whole novel that I pointed you at. So just look at this and see if it makes sense. But by and large, you don't have to worry too much about this and this. All right, I'm going to end this slides on that note.